Hello everyone, I'm Frank and welcome to Frank Puzzles, and this is today's hard level difficulty puzzle, and it's called Rat Run 36, Alternating Current. Alright, I guess I should actually pronounce it the real way, because actually that's actually correct. Alternating Current. These are known as black currants or red currants, and it's actually currant. Um, but I always pronounce it with the sort of Frenchified way of pronouncing it. I don't know. And nobody told me how it's pronounced, and then I basically started pronouncing it the French way. I don't know. And this is by Marty Sears. Anyways, here are the rules. We have Sudoku, where we need to fill the grid with the digits 1 through 9 so that each row n and column n contains exactly n distinct digits, with the rest of the cells in that row slash column being repeats. For example, only 3 distinct digits appear in row 3, and any of these can be repeated multiple times in order to fill that row. So you could have something like, say, 6, 8, 3, and then you can only have 6 8s and 3s remaining in that row. And so in row 1, you have only one distinct number, or distinct digit in row 1 and in column 1. In row column 2, you have 2 distinct digits. In row column 3, you have 3, etc., all the way up to row 9 and column 9, containing exactly 9 distinct digits. So that's how Sudoku works. Aim of experiment. F and P must both reach the cupcakes by finding a path through the maze. The paths must not visit any cell more than once, cross themselves or each other, or pass through any thick maze walls. The paths may only intersect at the cupcake cell. So, for example, you can't have F going this route, and then P overlapping or crossing any of that route. So this would not be allowed, because they would be sharing cells here, and they can only share cells at the cupcakes. As well as moving orthogonally, they may move diagonally if there is a 2x2 space in which to do so, but may never pass diagonally through a round wall spot on the corner of a cell. So, for example, you could have P going something like this. Oops. We have P going something like this, and she could do something like that. That would be perfectly valid. What she cannot do, though, is next go something like that, because it goes through a round wall spot on the corner of a cell, which is not allowed for the rats to go through. They can go like that. Okay, we have black currants. I guess I'll be pronouncing it correctly, since it's actually used in the title as a currant, where if a black currant sits between 2 digits, one is double the other. We also have red currants, where if a red currant sits between 2 digits, one is odd and the other is even. So for example, say this was a 2 here. Then this digit would have to be 1 or 4 to maintain the 1 to 2 ratio between them, because there's a black currant between them. And this could be 1, 3, 5, 7, or 9. Since this 2 is an odd even digit, the other digit has to be an odd digit next to it as a red currant. And that's an example of how black and red currants work. We have also grapes, where if a grape sits between 2 digits, they have a difference of at least 5. So, for example, if this were 3 here, this would have to be an 8 or a 9, because the only digits which are 5 or more away from 3 are 8 and 9. So, That's an example of how grapes work. We have cages, where digits may not repeat within a cage, so these cannot have repeats, even though you can have repeats in rows and columns. But in a cage, you cannot have repeats, and each cage has the same total to be deduced. If the digit on a cage's electricity symbol is 5 or higher, the cage may not be entered. The electricity symbol is 5 or higher. It cannot be entered. So if this were, say, a 5, then no rat can actually enter this cage. So you could not actually enter this way and go through the cage if that were the case. Also, again, each cage has the same total. So keep that in mind. And that's only a 5 on the electricity symbol of the cage. Right? You could have a 5 or higher in the other cell in the cage for these cells. But if it does have a 5 on the electricity symbol on the cage, then the rats cannot enter those cages. Test constraint. In this experiment, both rats visit the same number of cells. So therefore, the rats must go have the exact same number of cells on their paths to the cupcakes. Any pair of cells, one on each path, that are equal distance from the cupcake cell, sum to the digit on the cupcake cell. Thus, both paths combined form a valid zipper line with F and P at the ends and the cupcake cell in the middle. So say this was at 8 here. Then these two digits on F and P would have to add up to 8. So you could have something like 3 and 5 here. And that would add up to 8, and that would be valid. And that's for every path, every cell that's on the path for F and P. So then say if F went this route and P went this route, then these also must add up to 8. And these also would have to add up to 8, etc., etc. Well, whatever the digit in the cupcake is, essentially. Anyways, those are all the rules. If you like to play along, there's going to be a link in the description. And now, I'm going to get started. Let's go. Okay. That means the cupcake. Okay, so we don't know which way the rats go. It's probably not going to be 3 or 4. Okay, so in row 9 and in column 9, we're going to have distinctly different digits. In row 1, in column 1, we're going to have the same digit. So these are all the same digit here. We don't know what it is, though. In row 7, we have a full line of red currants and black currants. And we have 7 distinct digits. So one digit... In row 2, we have 2 distinct digits. And they must be 5 or more apart from each other. So one of them is going to have to be green, and we don't know what the other one has to be. Okay. So F and P are both going to have to go 2 So, okay, first of all, let's do the digits next to... Ah, that's pretty unique. The digits next to black crop key dots must be 1, 2, 2, 4, 3, 6, or 4, 8. So that's 1, 2, 3, 4, 6, and 8. Well, this digit, we have in row 7 a guaranteed 7 unique digits. And these are only 6 unique digits here. So that means the remaining digit here has to be 5, 7, or 9. So since this is 5, 7, or 9, that's next to an even digit for the red Currant. And you can't have 5 here, because 5 can never be 5 or more away from another digit, right? If you subtract 5 or more from 5, you get 0 or less, which is not a normal Sudoku digit. If you add 5 or more to 5, you get 10 or more, which is not a digit. So this must be 7 or 9 here. That makes this 2, 4, 6, or 8 here. To be in a 1 to 2, or to be even to the 7 or 9 odd. This has to be a low digit here because we have a 7 or 9 here. So we have 1 to be 5 or more away from 7 or 9. We have to have a low digit 1 through 4 there. 3 cannot be here because that would force a 6 there to be in a 1 to 2 ratio. So we have 1, 2, 4, 6, and 8 here. So the digit in column 1, which is going to be the same throughout, has to be 1, 2, 3, 4, 6, or 8. So we know in row 7, none of the digits are going to be a 5. Can we have a 5 anywhere else in these rows then? I think the answer might be no, but that might be... This digit can't be 5. So these digits have to be 1, 2, 3, 4, 6, or 8. Technically, you could have 1 and 2 adding up to the cupcake. It's very unlikely. So then that would add up to 3. It's you cannot have 5 here because it's 5 away from another digit. So we have 1, 2, 3, 4, 6, 7, 8, and 9. It's very unlikely to be 3 or 4. It cannot be 3 or 4. So, yeah. If it's... Well... Okay. So, if it were 3, it cannot be 3. Because in row 9, F is going to have to go in one of these cells, and that must add up to that digit. So it's less than, it must add up with where P goes to that digit there. So this cannot be 3 here, because we have 3 digits guaranteed in row 9 to be less than that digit. However, technically we could have F going that way and P going that way. And that could add up to 4 potentially. So we have 4 there. These two must add up to 1 and 3. So we would have to have 1 there, 3 there. This could be 2 and 2. But then the problem is P would have to go that way and then would have to go there, which means it would be guaranteed to be 7 or 9, which it would have to go through, which would then does not add up to 4. And the other way is P goes this way. We have 4 unique digits because, again, every row 9 has to have 9 unique digits in that row. and there's 9 spots. So yeah, it cannot. Okay, so this cannot be 4 here. It's 6, 7, 8, and 9, which means it's 1, 2, 3, 4 there. Um, hmm. Hmm. The interesting thing is, if F goes this route, what does that imply? That means P has to have 3 cells in a row, which are all the same digit. Is that possible? I don't think it is. Right? So if P goes this route, okay. If P, okay, so P cannot go this route if that's the case. Because these are guaranteed, all 9 cells in column 9 are guaranteed to be distinct because we have to have 9 distinct digits in those columns. In column 9 specifically. So then P could go here. It can't go to the rest of row 9 because those are distinct digits. So these would have to be the same. And then this would also have to be the same. But that's not possible, right? You have 8 unique digits in column 8 and row 8. So therefore you only have 2 that can be the same. And it's the same way if you try to go the other path, right? If you try to go this way, that's 3 unique digits. Oh, that's not true. Okay, so these would then all be the same. This would have to be different. Therefore, you would have to go that way if that were the case. So that would be different than that. Um, hmm. Interesting. Hmm. So one thing we cannot do is F cannot go all the way through here. Okay. So then we can block off this area. Oops. And this area from ever being entered. Um, well, technically, she could do something like this, right? Okay, so I'm not going to rule that out. Okay, so interesting. Um, hmm. Huh. What other thing can we assume? Can we assume anything? I don't even know. Oh, cages. So this cannot be green. This has to be a different number, because in row 9, same with that. Right? So this is definitely the different one than... So this is either green or these are the same digit. So that's possible. Or they could be technically different digits, right? We don't know. Um... Every cage adds up to the same sum. So this is one digit adding up to these two digits also. So this could be 3, 4, 6, 7, 8, 9. And you can never have a 9 in a cage. That's interesting. Because, or 9, except for here, I guess, right? Um... The interesting aspect, though... So can F ever go all the way over here? If F does that, P has to go this route then. But the problem is we need a 9 somewhere in row 9, so therefore this would be 9. So that's not allowed, because this digit cannot be 9, because it's next to a black crop key dot. So F is either going this way or this way. And we can never have... So this can never be 9 here. I guess P could go this way, and then one of these is 9. But we don't know. This again is 1 through 8 here. So if PF goes this way, she has to go there. She cannot go all the way here, so she either goes this way or enters this way. Now that's interesting. If she enters this, all the other cages must add up to this digit, which has to be lower than 5. Huh. And this would be 3 or 4, so this would have to be a high digit. So if F goes this route, this is definitely 3 or 4. That can't be 4. It has to be then 3, which would make this 8 to be 5 apart from it. 8 would be in a 1 to 2 ratio with 4. And therefore these must add up to 3. So it'd have to be 1 and 2 always. So this can't be 1, 2 as a pair. And this 3 would eliminate 3 here, so that's 4, which makes that 9. 4 would have to be in a 1 to 2 ratio with 8. And the remaining digits in column 9 would be 3, 5, 6, 7. 9 would be here. 4 means this can't be 4. It would be 2. It would be 1 or 3. That's in a 1-to-2 ratio with only 2 or 6. 8 would mean this is again 1 or 3. So we'd have 1 and 2 here. 3 of these digits would be the same. 1 and 2. This is 1 and 2. 1 and 2. 1 and 2. 1 out of 1 or 2 is here. We have 6 cells, which could have to be different. Right now, we have a duplicate twice here. Uh, 1 and 3 is in a 1-to-2 ratio with 2 and 6 again. So this is that would force this to be 1 and 3. Which means this would again be 2 or 6 to be in a 1-to-2 ratio with that. Interesting. So this would be a 1-2 pair remaining in row 1 and 2 if that were the case. Ah, and that doesn't work. Because this is not going to be in a 1-to-2 ratio. Or sorry, can't be a difference of 5 between them, between 1 and 2. Right? 1 and 2 have a difference of only 1. So, F cannot go this route. Therefore, we know F's route. F has to go the opposite route. F then has to go this way. And again, cannot go that way because of how we were talking. So P has to go this way. These are all the same digit because they must add up to the cupcake digit. And these are all the same digit here. This is in a 1-to-2 ratio with that digit. So therefore, a P has to go here. F could potentially go down here and then go back up here. But F will eventually have to get to here. So therefore, this cannot be 5, 6, 7, or 8 because this must... F has to enter that way. There's no other route she can go. So these are all the same, which means these are all different. That's interesting. So this is odd. This is even. So these are different odds and even parities here. So let's start coloring one. This will make medium, dark. One of these is going to have to be double the other. So if this is odd, this would have to be even. Well, okay, no, we don't have that. It's going to... I'm not sure. So all of the rest of column 8 is different. All the rest of row 8 is different. All the rest of obviously row 9 and column 9 are different. Okay. So P cannot go this route because F has to go some route to the cupcake, and then so she has to go this way. So yeah, we are blocked from entering here, entering here. So P has to go this route. And she could still go that way or that way, technically. Mm-hmm. At least one of the rats is going to have to go in rows 2 or 1. So that's going to be interesting. F could potentially go this route. But it cannot be direct, I don't think, right? So we have right now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's not. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 cells at least on P's path. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. That doesn't work. But she could do something funky like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Nope. She has to go longer than that. 1, 2, 3, 4, 5, 6, 7, 8. Oops. 2, 3, 4. So she has to go. So F is definitely going that way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. That's possible. Can she go this way? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Yes, she could go that way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. No, 18. No, so she still can't go that route. So I think this is closed off. Right, because again, let's try 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So no, she cannot go this path at all. So this is going to be blocked also. Hmm. Can she go the direct path? Well, no, not the direct path, likely. Um, So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. So the most direct path, okay. For P, if F goes this route, is 28. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Oh, wait, I can go diagonal there. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So 26 is the most direct path. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22, 23, 24, 25. Well, she can't go that way. Hmm. Okay, what happens if F goes that way then? So say F does go this way. So she has to go that. P would have to could do something like that, I guess. That's pretty long. So obviously these two would add up to this. These two would add up to this. So this would have to be the same. So that would all be orange. Right, so okay. Even 3. I mean, it could technically be green and green adding up to that digit. That is possible also. Mm. Hmm. Or you could do something like that, right? I mean, green and green could technically add up to whatever this digit is. Okay. Um, so we don't know that. We do know that these all have to be the same. Um, it's not necessarily orange. It could be green. So you'd have technically you only need so you could have 1 and then 2, 3. So this would be actually you don't even need that. So you could have that technically. But you have to have these amount. Okay, so this would be, geez, this would be all the way here to there. So how many cells in a row do we have to have that are the same? Um, you could have one. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Hmm. I'm guessing though it's probably going to be this route, would be my assumption. Because I mean, otherwise, why would this whole area? Well, I don't know. You could go back and forth technically, like here, right? You could go here and then here. Um, hmm. So you could have 1, and then these are the same. So you have 1 at least. 2, 3, 4, 5, 6, 7, 8, 9, 10. So 5 more in a row. So here, we know that these two digits cannot be the same because these two digits are the same. So this has to be orange then. Okay, so for one thing then, we know this must be orange and this has to be red. Because we have 2 digits here that are the same. We have 2 digits here that are the same. Ah, and green and blue cannot be the same digit. Because we have 2 digits here that are the same. It's blue. And it cannot be the same as green because we have to have 8 unique digits in row 8. So, this is not blue. So, green plus blue adds up to the digit here. And that's actually, that shows then, that it can, FP cannot be going this route. If P goes this route, F has to go this route around. Or sorry, P is this one. F is here. If F goes this route, P has to go around this way. And the problem is green and blue add up to the zipper number here. So this would all have to be blue here to add up with the green to add up to the zipper number. But this can't be blue because it's either green or orange. And orange cannot be blue and green cannot be blue. So therefore, F cannot go this route. F has to go this route here. So F is definitely going this route. So obviously she has to go this way so that to extend the different distance of the path. Otherwise it's going to be too short. Can she 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So F could still go this route, technically. This cannot be green, so this can't be blue to add up to the zipper number or the cupcake number. Huh. So we know green, orange. We know green, orange or red, and blue are different numbers. Orange and red could be the same one. In fact, are very likely to be the same one. This is green. This has to be green or orange here. Green and orange Ah, green and orange have to be at least 5 apart from each other. So that means this is guaranteed for the sum of this cage here has to be green and orange. And that's difference of at least 5, so it's at least 1 plus 6. So this cannot be 3, 4, or 6. It's 7, 8, or 9, which is 5 or more away from 1 through 4 here. That means this cannot be 6 again, or this can't be 3 here, because 3 would force us to be a 6 to be in a 1 to 2 ratio. Hmm. Okay. Interesting. So these two add up to the digit here. These two add up to the digit here. So we know green and blue add up to the cupcake digit. Hmm. Ah, this cannot be green. Because if this were green, the problem is green and blue only add up to the cupcake digit. And therefore this would have to be blue, and that would have three copies in row 8, which means we only have at most 7 distinct digits in row 8, which is not allowed. So this cannot be green. It has to be red, which means let's color this something else. I guess dark. Dark then has to be here, because red and dark add up to the cupcake also, and they're distinct digits. So we could have red go here, but then that would mean dark goes that way, which is still possible. Um, these are green or red. We have green or yellow, green or orange there. We don't know which way red goes, or P goes. How many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, this is 7, 8, or 9. So F cannot go this route because she can't enter a cage with electricity symbol of 5 or higher. So F has to go this route. Interesting. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. If we try to go this way, 12, 13, 14, 15, 16, 17, 18, 19. So that would be enough for the totals there. So we could go this route here. Okay. So red and dark. We could have repeats here. Um, 1 through 4. Hmm. Obviously, this digit cannot be the same as that. But could be the same as that one. This could be green. So this is red and dark adding up to this. So this is not 5 or 7. So green and red both have to be 1, 2, 3, 4, 6, or 8. Okay. So we have guaranteed 3 reds here. Obviously, red could be the same as orange. We don't know. But we know we have a green-orange pair here. These could be all the same digit. We don't know. This cannot be red because these are different parodies. So, but this still could be green. Oh, so this is red. This cannot be dark. So this is 1, 2, 4, 6, 8. So this cannot be dark. It's a different digit, but it could still be blue. This cannot be blue. It can't be green or orange, but it could be red. We don't know. So we have 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This is 6, 6, 7, 7. So these two add up to this sum, and these two add up to this sum. These are different parodies. So these must be different parodies, right? Because again, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. This becomes 6 and 6, 7 and 7, add up to the cupcake digit. And this changes parity. So because this changes parity, this also must change parity. And the only ways that changes parity if it's 1 and 2, or it's 3 and 6. So no 4 and 8 here. Interesting. You could have 3 and 6 and 3 and 6 potentially there, right? And that would add up to 9. Um, can you add up to 6? No. if you try to add up to 6, that would be, you would have to have different parities, and none of them could be 5 or 7. How would you add up to 6 in both of those cases? You couldn't. Because you would have to have one set be 1, 5, and the other set would be 2, 4. But you have to have one that's an odd parity, right? 7 does work. What about 8? 8 does not. If you try to have 8, that would be 1, 7. You would have to have 1, 7, 2, 6, or 3, 5. But the problem is 3, 5 contains a digit that cannot be next to a black crop dot. 1, 7 also does. So the odd digits adding up doesn't work. So this cannot be 6 or 8. It's 7 or 9 here. Interesting. So this is 7 or 9, which means this digit is not, well, we already knew that. It's not the same, right? So we add up to 7 or we add up to 9. Therefore, you cannot have two of the same digit adding up to this digit. That's pretty clever. So you could have 1 and... How would that work? Can you actually add up to 7 here? I guess you could have 3 and 4, right? 3 and 4, and then 6 and 1. That is possible. Okay. 3 and 4 and 6 and 1. Yep, yep. It cannot be 2 and 5, obviously. What are the other possible combinations? 1 and 8, 3 and 6, 2 and 7 cannot, and 4 and 5 cannot. Interesting. Yeah. So 2 can never be in this set of digits, the digits that are adding up to... Well, this could be 7. So green could be 2. But red and dark are both in a 1 to 2 ratio with another digit. So they can't be 5, 7, or 9. So you cannot have 4, 5, and you cannot have 2, 7 adding up to 9. What about adding up to... what is it? Okay, so another thing is this can't be 1 or 2 here. Because if this is 1 or 2, it adds up to at most 4 plus 2, which is 6, which we know this is 7, 8, or 9 here. Because again, the difference between these two digits is 5 at least. Because of the grape that's in the row 2. Okay, so we cannot have 2, 5 adding up to 7. We can't have 2, 7 adding up to 9 for the red and the dark cells. We could have 3, 4. We could have 1, 6. We could have 1, 8. And we could have 3, 6. So there's no 2 here and no 2 here. Because this can't be 2. This can't be 1 here. Because 1 can only be in a 1 to 2 ratio with 2. So this is not 2. It's 1, 4, 6, or 8. This has to be not 2 either. 1, 3, 4, 6. So this is not 2, which means this can't be 1 here. So the green has to be 2, 3, 4, 6, or 8, interestingly enough. Therefore, orange cannot be 8. Red cannot be 8. Because if red were 8, 8, and 1 would have to add up to 9. 4. Oh, that's not true. Red could still be 8 because red and the dark have to add up to 9 or 7. So red still could be 8. Never mind. Okay. Hmm. We have in row 7 2 duplicates. Okay. We don't know which ones they are. Okay. Hmm. It's very possible that this digit is the same as the cupcake digit. Um, that's possible. So blue could very well be 7, so that doesn't help with the 2. Blue could also be 5, so that's fine. Okay, so we have this is 6, 7, 6, 7. Okay, what happens if P goes this route? Then that means this is 7, this has to be 9 for it to add up to. So let's see. How would that work? If P goes that way, this is 5, 6, 5, 6. This would be 7, 7. So 5, 6, 5, 6, 5, 6, 7, 8, 7, 8. So this would be 7. This would have to be 9. 7, 8. So 7 and 2 add up to 9, if that's the case. 1, 2, 3, 4. This would have to be 1 and 3. Because to add up to 9, we need, this is even. And so it'd be 6 or 8 there, which would make this 3 or 4 there. To add up to 9, so this would be 3 or 4 to be in a 1 to 2 ratio with 6 or 8. 3 and 6 add up to 9. So this would have to be 3. So then we'd have 6 there, which would make that 3. And this would have to be 6, which would be in a 1 to 2 ratio with 3, but we don't have all the distinct digits there. In row 7, we have 3 copies already, which is not possible. So we cannot have, P cannot go to this 7 here then. So P has to go this route. Okay. So if 6, 7, 6, 7, 8, and 8 are the same, 9 and 9 add up to the same. So this cannot be 1 or 2. It's 3 through 8 again. Plus this to add up to 7 at least. Hmm. So these two add up to the cupcake digit. Hmm. So what's the most that f can go to? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So that's the most that f can go to. One, again, just double check. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So can p ever go this route? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Yes, she can. Ooh, okay. Um, hmm. So the max path we have is 22. The minimum, I think, is 17. Is that right? 1, 2, 3, 4, 5, no, 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So the minimum path is 18. The max path is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So the minimum path is 18. The maximum path is 22. Interesting. Okay. One thing we know is, well, that's not true necessarily. Hmm. We know this is not dark, but it could be blue. In fact, it's quite likely to be blue, maybe, if this is green. So these two add up to the cupcake value. These two add up to the cupcake value. We could have duplicates of green and red in either of them. Or they could be completely different. That's part of the issue. Um, okay, what digits can this be? These two again add up to 7 or 9. If we have 2 here, 2 and 3 is too small. And 2 and 6 adds up to 8, which again, this digit cannot be because we have to swap odd parities here, and that means we swap parities here. To add up to the same sum. So 2 and 6 doesn't work. 1 can be with 6 here to add up to 7. Um, 2 cannot be here either. If this is 2, so these are opposite parities. So let's just mark those. I guess light and medium. These are opposite parities, so therefore this must be medium, and this is light. So these are opposite parities. This is medium there, which makes this light there. Okay, so we have medium, light, medium, light. These are opposite parities, so this is medium. So we have medium, light, medium, light, medium, light. We don't know about green. So can this be 2? So 1 can be with 6 or 8 here. 2 cannot add up to 7 or 9 here, so no 2. 3 can be with 4 or 6, and 6 can be with 1. So if this is 1, 2 as a pair, this must be 2 there. How does that work? Again, this can't really be 2. To add up to 7 or 9, 2 would not be 4, 6, or 8. So this cannot, this is 1, 3, this is 3, 6 as a pair. So this is guaranteed to be 3, 6 as a pair. 3 and 6 and 8. 3 and 4 add up to 7. 3 and 6 add up to... So this cannot be 8 here to add up to 9. So 3 can be with 4 or 6 adding up to 7 or 9. 6 can be with 1 here adding up to 7. 1 means this can't be 1 here. So 1 and 2 is fine. 4 and 2 is fine. This can't be 4 because 4 would have to be in a 1 to 2 ratio with 2 or 8, and this can't be 2 or 8. 1 and 6 works. 2 and 3 does not, so this can't be 2. 3 and 6 works. 4 and 3 works. 6 and 3 works. 8 cannot be here. Interesting. So, and this can't be 6, because if this were 6, you would be 6 guaranteed here. But... okay, this can never be 3. If, again, we'd have the same problem, right? Well, we have 3 and 6 there. That means this cannot be 6 and 6 to add up to 7 or 9. So this is 3 and 6. That's 6. So this is 3 and 6 add up to 9. This must be 3 and 6 adding up to 9. And we have too many duplicates again in row 7. So because of that, this cannot be 3. This is 2. Therefore, that's in a 1 to 2 ratio with 1 or 4. Well, if 3 is here and 1 is here, if 3 is here, 1 is here, sorry, 3 is here, 4 is here. If 6 is here, 1 is here. This adds up to 7. So this has to be 7 here. That means everything on the line cannot be 8. Because they must add up to 7. So no 7 or 8 here. This can't be 7 or 8 here. So this is 1 and 4 to add up with 3 and 6. Whereas the 8 in the row, we have to have an 8 because we have to have 7 unique digits. So this is 8 here, which is in a 1 to 2 ratio with 4. That makes this 1 there. 1 and 6 adds up to 7, and 3 and 4 add up to 7. So no 8 here. No 8 here. So this is either 1, 6, or it's 3, 4, adding up to 7. So this is 1, 3, or 4. So that means we cannot have, we have 2, 3, 4, 6 in green. So this is 4. 1, 3, or 6 here. We have 6 and 7 here. And the last digit is 1 or 2. So the remaining digits in column 3 are 1, 2, 6, and 7. 1, 2, 6, it cannot be 7. 1, 2, 6, 7. 1, 2, 6, 7. In column 3, well, if this were low, this would have to be 6. Actually, this can't be 6. If this is 6, that would force this to be 1. And 6 and 1 add up to 10. So this has to be 1 or 3 there, which works. Which 1 and 3 is in a 1 to 2 ratio with 2 and 6. Okay. No 8 here. This is 1, 4, and 6. 1 and 4 are in a 1 to 2 ratio with 2. 6 is in a 1 to 2 ratio with 3. So this can't be 4 there. It's 2 or 3. So this is 1, 3, or 6. It's red. Again, if 6 were here, the problem is that 6 and 1 is the only set that can be 5 apart from each other for 6. But 6 and 1 also add up to 7, which is not allowed. So this must be 1 or 3 here, which makes this 6 or 7 there. So that means dark is 4 or 6 here. Okay, so we have all the coloring for the light and medium set. So light cannot, whoops, this can't be medium. And these can't be, well, let's clear those. No more medium. No more lights. Okay, so this is red. So no 6 there. It's 1 or 3. So, green is 2 or 6. That's interesting. Okay. That means blue has to be 1 or 5 to add up to 7 with the green. Okay. We have 1, 2, again. So red is 1 or 3. Let's remove these. Again, size 18 or 22. Remaining digits of column 1 are 2 and 6 again. So green is 2 or 6. I guess we don't really have to fill those out. This is 1, 2, red is 1 or 3. This can't be 6 here. 1 and 3 are 5 or more. This has to be, red has to be 1. It's because 3 is not 5 or more away from 6 or 7. So 1 and 6 add up to, so therefore this is 1, that's 1. So no more 1s in row 8 and 9, so those are all 5s. So therefore green has to be 2. So green is 2 here. We must add up to 7, 8, or 9. So it must be with 5, 6, or 7 there. 6 cannot be here because of 6 in the column. 2 eliminates 2 in the rest of the column. So this is 3, which is 5 or more away from only 9, not 7. So this is 9. All the greens are 2. So these are all 2. 6 eliminates 6 in the rest of row 9, so it's 7. No more 1, 2, or 6 in row 8 because we already have duplicates, so this is 7 also. That eliminates 7 and 8 in for this, because this cage must sum to the same as this cage, and it's either 2, 5 adding up to 7 or 2, 7 adding up to 9, but the 7 in the row eliminates 7 in the rest of the row, so this is 9, which means orange is 7. So this must be 7 there. So this is 1 or 2. So this cannot be orange here. It cannot be red. It's definitely green, so this cannot be green here. It's orange. So this is 7. So the P cannot go into 7. So this is 2 here. That's 5 apart from each other. Oh, yeah, right. It had to be 5 apart from each other. Okay. So that means P does have to go around. So it's... But I don't think she can go to 22. 1, 2, 3, 4, 5, 6, 7, 8. She can't go through here. So she must go through here. So this is 2. So that's 2. That's 2 duplicates in column 7 and 2 duplicates, or 1, no, just, sorry, 1 duplicate in column 7. So this is 2 or 1 to be 5 apart from 7. And this is 1 or 2. So that means whichever path that P takes, F has to be 6 here. So this is 6. It's gonna have to be a lot of 5s. This digit is 4 or 8. We're not sure which. How? Oof, we have to go around. Okay, so what's the minimum now? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Can we do that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15, 16, 17, 18, 19. Ooh. That ain't great. That ain't great. We can go that way, though. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So she has to go that path. That's the minimum. And we have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So the minimum now we have... So this... P cannot go this route. Because if P goes that route, the minimum that route is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. And then this, but this cheat F does not go for 21. if P goes this route. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Right? So F has to go this route. So F has to go here, 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 and then some order here. I'm not sure. To avenge... Actually, she could do 20... More than that? How many is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. She could go 23. Technically. Okay. Oh boy. Remaining digits of row 9. We have 3, 4, 8, and 9. Okay. Remaining digits of column 9. We have 1, 4, 5, and 8. Okay. Oh, it has to be in column 3. We already have 2, 6, and 7. So that means the remaining digits are 2, 6, and 7 in column 3. So P cannot go this route. P definitely goes around this way. So P has to go that way. P has to go that way. So we have a whole bunch of 5s we need. So row 7 is done. Row 8 is kind of done. Row 9 is kind of done. Column 9 is kind of done. Oh boy. Okay, so we don't need the coloring anymore. So that's not... Let's remove the coloring then. This adds up to 7. We can have 3, 4, 5, 6 there, which means this is 1, 2, 3, 4 as possibilities. Wait, hold up. No, this has to be 5 or 6 here. Because again, it has to be with 1 or 2. These are 2 and 7 in row 2. 1, 4, 5, 8. We can have up to 3 repeats in row 6. So again, these digits must be 1 through 6 on the path. You could technically have 1, 1 here, so this could be 6, 6. This is 1 through 6. These 2 digits have to be 5 apart from each other, so that's 1 and 6. Because the only digits which add up to 7 are 1 through 6. So we have guaranteed these digits have to be 1 through 6, because they are all on the path except for these 2, which we know are 2 and 2. Okay, well, we know this is on the path. So we know, yes, red has to go that path. So this cannot be 3 or 4 because we have too many duplicates already in column 6 if it were. So this is 8 and 9, which has to be with 3 or 4 here. Okay. Um, so we have, okay, remaining digits of column 8. We have already two fives, so that we have the duplicate already there. So the remaining digits are 1, 3, 4, 6, and 9 as possibilities. Um, Anything on the path cannot be 9. Okay. So this adds up to 7 with this digit. Right. So maybe we should label these with letters. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So these are both A's. So the A's add up to 7. The B's add up to 7. The C's add up to 7. D, E, F. We don't know about that. So B's add up to 7. It has to be 1 and 6 as a pair. We don't know which one, though. So this cell has to be the same as this cell. So these are the same. We'll mark those as yellow. Because if this is 1, this is 6. And this has to be 6 to add up to 7 with it. What else do we have? There's a lot of 5s there. Um, hmm. We have so 1, 2, 3, 4, 5, 6, 7, 8. So that's at most 8 away from the cupcake. So 1, 2, 3, 4, 5, 6, 7, 8. It could be 7 or 8 away here. 1, 2. So 1, 2, 3, 4, 5, 6, 7, 8. 8, no matter what, is going to be 2. So this has to be a 5 here. And I think this has to be 5 also. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, wait, hold up. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 up to 9 has to be at least 5. So we have to have 5 there, 5 there. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we don't have to have 5 there, but we do have to have 5 there. Assuming we go that route. So there's going to be a lot of 5s here. This could be 6. We are guaranteed one of these two has to be at least on the path. Because otherwise this is not going to match. So we have A, B, C. You could have D, E, F. So that's not going to work because that's 1 or 6. So if we try to go D, E, F, that doesn't work because 2 doesn't add up to 7 with 1 or 6. So we have to have... This could be F. So F, we have 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So so how many steps left do we have to the cupcake from here? Because this can't be 2 because of the way that column 8 works, because we already have the duplicate there. So it can't be 2, can't be 5. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 guaranteed steps. So 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that matches exactly. So then we have to go the minimum distance. So we cannot go this path. We have to go this way. So we have to go this way to not there, to here, go there, and then go there. So then this must be a 1. So that means 6 and 1 add up to 7, 2 and 5 add up to, and all of these actually have to be 5 because we don't have enough enough paths to do that. Therefore, F has to go here. So this must be 1 and 6 as a possibility. These have to all be 2 because of the way that it works. This is 5 here. We have 1 duplicate, 2, 3 duplicates, and then 4 duplicates in column 5. That's all the duplicates we can have. So this cannot be 9 here. We have all 5s here. We have a 3 here. And this is guaranteed to be 4 or 8. That's all 4 unique digits in column 4. So this cannot be 7. It's 2. This has to be 2 or 3, which adds up with 4 and 5 to add up to 7. That's not going to work. We already have 2 duplicates in column 7. Dang it. We need a 3. So this has to be 3. That makes that 4. Oh, 4 works. Okay, there we go. Right, because in column 7 we already have 2 duplicates, which we can only have 2. Every other digit needs to be unique. Or distinct. So that's 1, 6 eliminated, 2, 4, and 5 eliminated, so that must be 3, which makes that 4 to add up to 7. So we have 4 and 3 here. We have to go through all of these cells. So there's no way we can't do any diagonal shenanigans here. So this has to go this way, because it has to enter and then exit. That means we have to go that route. So this is F. This must E is one of these, and then D is one of these. We don't know which. Okay, F. So this is 8 or 9 again. We have C, D, and E. Okay, so we have guaranteed 5, 7, and 2 unique digits as unique digits in row 4. So the last one must be 1 or 6. So we cannot have a non 1, 2, 3, 1, 2, 6, 5, or 7. So that eliminates 3 and 4 and 9 or 8. Okay. We have 1, 2, and 5 already in row 3. So that means the rest is 1, 2, and 5. So this has to be 1, and this must be 1. Or 5, actually. I guess it's 1 or 5. Well, we have a 1, 5 pair in column 9, which eliminates 1 and 5 in the rest of the column because they must be unique. So this is 4 and 8. We have 2, 3, 4, 5 already in column 4. So that means the rest must be 2, 3, 4, 5. So we have 4 there, and this is 3 or 4 here. We have a 3, 4 pair in row 9, which eliminates 3, 4, and 8 in the rest of the row. So this can't be 3, 4. It's 8. That means this can't be 8. It's 9. Okay. So this is F. That's 1. So that makes this. So the yellow both have to be 6. Which means B here is 1. And 1 and 6 add up to 7. 3 and 4 add up to 7. C is... We don't have any more duplicates, so 1 eliminates 1 here, so that's 6. No 1 or 6 here. It's C, which is 3 or 4, which means this is 3 or 4 to add up to 7. No 1 or 6 here. It's 3, 4, or 9. We have 2, 5, 6, 7 in row 7. So that means there are no more other digits. We have all the unique digits. So therefore, this is 2. No, this is 2. This is 5. And this is 2 or 5. 5 eliminates 5 here. So that's 1. E is 2 or 5. So this can't be E. This can't be E. So E has to be here. Wait, that doesn't work. No, everything was working fine until then. Shoot. Let me double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Shoot. Oh, wait, this could be 6. It could be 6. It could be 6. Okay. Okay. There we go. That's, yeah. I think I removed 6 as a possibility. Yes, so this has to be 6 because there's no other way it can get through. So then P has to go this route, which means she has to go there, which means she has to go there. So then this is 6. Okay, there we go. Which means this must be 2 here to add up to with 7, 5 with 7, and C are here. How many duplicates do we have? We have 2 duplicates in column 6 and a third one. So these are distinct digits. Okay, so move that. This will be yellow. This will be orange. Orange and yellow add up to 7 because they are distinct digits. That means this can't be or yellow. It's orange there. Oh, sorry, pink there. I keep saying orange. I don't know why. And now, so we have all the paths. So let's just double check. 6 and 1 add up to 7. 2 and 5 add up to 7. 5 and 2 add up to 7. 5 and 2 add up to 7. 6 and 1 add up to 7. 6 and 1 add up to 7. 3 and 4 add up to 7. 4 and 3 add up to 7. 6 and 1 add up to 7. 3 and 4 as a pair somewhere are going to add up to 7. 2 and 5 add up to 7. 6 and 1 add up to 7. 6 and 1 add up to 7. 5 and 2, 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 2 and 5, 2 and 5, 2 and 5, 1 and 6 all add up to 7, which is 5 apart from 2. 2 and 7 are 5 apart. 2 and 7 add up to 9. Oh, these have to add up to the same sum. So this must be 2 and 7 because that's the only possibilities for those cells. So 2 and 7 there. 5 and 4 does add up to 9. That's good. 2 and 1 are in a 1 to 2 ratio. 6 and 1 are 5 apart. This is 6 and 1 there. So that's 5 apart. How many duplicates do we have? So 1, 2, 5, and 6. That's 4 distinct cells. We need 1 distinct cells for the remaining digits, and this is going to be distinct no matter what. So is this, so they must be the same digit. So yellow has to be 4. That means this is 4 here. This can't be 4 here. It's 8. That means pink has to be 3. So pink is 3. And okay, so we added up the paths. The paths work. 2 and 7 add up to 9. 9 adds up to 9. 2 and 7 add up to 9. 4 and 5 add up to 9. We go this path, so therefore we can go through that cage because it's less than 5 in the electric symbol. 2 and 7 are 5 apart. 2 and 7 are 5 apart. 1 and 6 are 5 apart. 1 and 6 are 5 apart. 2 and 9 are 7 apart. 1 and 7 are 6 apart. 4 and 9 are 5 apart. 3 and 9 are 6 apart. 9 and 8, 9 is odd, 8's even. 8 and 4 are in a 1 to 2 ratio. 4 and 1 are odd and even and odd. 1 and 2 are in a 1 to 2 ratio. 2 and 3 are even and odd. 3 and 6 is a 1 to 2 ratio. 6 and 1 are even and odd. And 1 and 2 are a 1 to 2 ratio. And unique digits. 2 in column 1. 1 and 2 in column 2. 2, 6, and 7 in column 3. This is not 4 because of 4 in the column. So 2, 3, 4, 5 in column 4. 2, 5, 6, 8, and 9 in column 5. 1, 2, 3, 4, 5, 6 in column 6. 1, 2, 3, 4, 5, 6, 9 in column 7. 1, 2, 3 or 9, 4, 5, 6, 7, 8 in column 8, and we have all the unique digits in column 9. 2 in row 1, 2 and 7 in row 2, 1, 2, 5 in row 3, 2, 5, 6, and 7 in row 4, 1, 2, 4, 5, 6 in row 5, 2, 3, 4, 6, 7, and 8 in row 6. So this is going to be a 3. We have 1, 2, 3, 4, 6, and 8, and 9 in row 7. 1, 2, everything but 8 in row 8, and then everything in row 9. So this is a 3. Experiment completed successfully. Test date April 29th, 1975. Cells visited 45. Black currants eaten 2. Red currants eaten 2. Grapes eaten 0. Inactive cages entered 1. What lay inside storage room A hit me like a punch to the gut. The largest cupboard had been completely cleared out and fitted with a huge, crudely built metallic circular frame, a thick bundle of cables. And fitted. The largest cupboard had been completely cleared out and fitted with a huge, crudely built metallic circular frame. Okay. A thick bundle of cables ran from its base into a compact power unit mounted against the rear wall. Though the controls remained set, the system was no longer receiving any power. It was instantly apparent what his intentions had been, and months of uncertainty were replaced with a sudden clarity. If there had been any lingering doubt, it evaporated when I found a near identical setup in room B. Excuse me. The second room bore greater signs of distress. A stack of boxes had been knocked over, their contents scattered across the floor, and the surrounding surfaces were faintly scorched, more so than in room A. The air carried an odor unlike anything I have smelt before. Shouldn't it be smelled? Smelt is a verb where you smelt something, but it smelt like a some sort of metal or something. Anyways, noticing a dark, smudged handprint on the wall by the door, I find myself retracing his final steps in my mind. I have no clue what this is, but okay. Very cool. Um, that was interesting. Very, yeah, it was hard level difficulty. Um, would I classify it as very hard? I'm not sure. I'm not the best with some doku, so for me, like I don't have the intuitions necessarily down for some doku. Um, but yeah, I mean, it seemed fine. I never felt really stuck, I guess. Um, yeah. Anyways, I hope you enjoyed this solve, and I'll see you next time on Frank Puzzles. Take care.